So one way to form epoxides is by making bromohydrins, and then from the bromohydrin doing that intramolecular Williamson ether synthesis with base. But the other way is to form it directly with what we call peroxy acid. And one of the most common peroxy acids does a really nice job of this is mCPBA, which stands for meta-chloroperoxybenzoic acid. So the first battle is remembering that mCPBA stands for meta-chloroperoxybenzoic acid, and the second battle is, all right, what the hell does that mean? Peroxy acid is just, instead of a COOH, it's got an extra oxygen in it. So we got that oxygen-oxygen single bond, and those are weak, which means that it's going to readily donate an oxygen. And then the meta refers to the fact that the chloro is on the 3 position. So really the correct name for this would be 3-chloroperoxybenzoic acid. But you'll usually see people using that ortho, meta, and para for position 2, position 3, and position 4. So there's where the M isn't capitalized, the rest of it is, because the meta, ortho, and para is never capitalized, even when it starts a sentence. So this is the reagent, and the key is that that oxygen there is the electrophilic oxygen. So that oxygen is what's going to be being attacked, but you'll notice there's also a lone pair on it. So it acts as a nucleophile and an electrophile simultaneously. So the mechanism is somewhat similar to the mechanism of addition of the mercuric ion to form the mercurinium ion, or the bromine to form the bromonium ion. But there's a lot going on around the ring as well, simultaneously. So we have our carbon-carbon double bond, and it doesn't really matter for the purposes of the mechanism. So I'm just going to show a really simple cis double bond with R groups. We have our electrophilic oxygen, and we have our benzene ring. Oops, we have our carbonyl group too, which I didn't draw. And then we have our benzene ring with the chlorine on it. This back part is just sitting there. You could actually call it AR if you wanted to. AR stands for aryl, and that means a benzene ring with something else attached to it. So we've got the lone pair and we've got the pi bond, which means the pi bond can attack the oxygen and the lone pair can attack the carbon at the same time in this 3-membered ring. But you've got to break these two bonds, the oxygen-oxygen bond, which is weak, and this oxygen-hydrogen bond. So in addition to the 3-membered ring transition state that's forming on the side where the oxygen is being attacked by the pi bond, we've got a 5-membered ring here where the oxygen-carbon, oxygen-oxygen, hydrogen electrons can flow around. So the carbonyl group is actually going to pluck off the hydrogen, returning that pair, right? The lone pair that's attacking the carbon here is going to be replaced by this pair of electrons. And then we're breaking the oxygen-oxygen bond and pushing this pi bond back onto the oxygen to replace this lone pair. So we've got all sorts of things going on at once in the transition state. And I'm going to redraw so I can show the transition state on the same page as the intermediate, and I actually have the carbonyl group. But this time I'll call that AR since that's not involved in the reaction. So mechanistically there's a nucleophilic attack on the oxygen electrophile, which has the partial positive. There's a nucleophilic attack of that lone pair, and then we're pulling off that hydrogen, breaking that bond and returning a lone pair. So there are actually 4 bonds breaking and 4 bonds forming simultaneously in the transition state. The pi bond here is breaking. We're forming a bond from that carbon to oxygen and from that carbon to oxygen. So there's the 3-membered ring part. And then we're breaking the oxygen-oxygen bond and the oxygen-hydrogen bond from that peroxy acid. Right. We're forming a new pi bond here. We're breaking the pi bond here, and we're forming a bond from that oxygen to the hydrogen. And then we've got our AR group. So it's a mess, right? Breaking 4 bonds, the carbon-carbon pi bond, the oxygen-oxygen sigma bond, which is weak, the oxygen-hydrogen bond from the peroxy acid, and the carbonyl group. And we are also forming 4 bonds, carbon-oxygen bonds for the epoxide. We're forming a new OH bond here, and we're forming the pi bond on the other side. And when we draw the result of all that, now we've got an epoxide, and the other product is an ordinary carboxylic acid. So it's almost like a lasso where this just lassos out that oxygen and creates a new carboxylic acid. But you'll notice that the oxygen that used to be the carbonyl is now the oxygen that has the OH group on it. There's a transfer of the hydrogen, and that's one of the reasons why this reaction works so well. You'll also notice that in this ring here, I've got kind of 6 electrons moving around the ring. This pair of electrons, the pair that used to be the oxygen-oxygen double bond, and this pair that used to be the pi. So that's an aromatic transition state on this side, on the 5-membered ring side. And aromatic transition states, when we have 6 electrons flowing in a ring, tend to be particularly stable, so that stabilizes the transition state as well. So it's a messy transition state, but it's a 1-step reaction. It's concerted. So we have to show the transition state, right? We always show the transition states when we have concerted reactions. And then this meta-chlorobenzoic acid, as opposed to meta-chloroperoxybenzoic acid, is usually removed by either filtration, depending on what the solvent is. It's much less soluble than the peroxy acid. So if you use ether as the solvent, for example, the meta-chlorobenzoic acid just precipitates. Or you do like a workup with bicarbonate, and bicarbonate deprotonates this and causes it to go into the aqueous layer. The epoxidation with peroxy acids, because the peroxy acid is large, epoxidation with peroxy acids puts the epoxide on the opposite face, as it puts the oxygen on the less hindered side. Of the original carbon-carbon pi bond. And that's because the reagent is bulky. So if we were to work with that Norbornane system, right, where we had the bottom face being more hindered and the top face being less hindered, and we were to do this reaction with mCPBA, the usual solvent is dichloromethane. The solvent dichloromethane is not involved, so when you're writing this mechanism, you really like to avoid using that CH2Cl2. And that will put the oxygen on the less hindered top face. Which is the opposite from where the bromohydrin put it. So that's powerful because it allows us to choose which face we want to put the epoxide on by simply changing the reaction conditions. Once you have that epoxide, of course, you can now protonate it under acidic conditions and open the ring at the more substituted end, or you can use strongly basic negatively charged reagents and open the epoxide at the less substituted end, so it's an entry to a lot of other compounds. But this transition state, people sometimes have trouble drawing, so I wanted to show it to you one more time. Questions? Comments? We've got 3 more classes. Tuesday we'll have our last quiz. It'll be a reactions quiz, maybe with a mechanism as well. And then there's no new material after break that will be covered on the 3rd exam. I'm just going to do a little bit of polymer chemistry. We have an exam the Thursday after Thanksgiving. The best way to prepare for the 3rd exam is to do the suggested problems. The suggested problems are good. There's a lot of interesting questions there. So if you haven't started doing the suggested problems, you should probably start doing those. The best way to prepare for the final, which is the American Chemical Society exam, will be to go through at the end of each chapter. There's a set of pre-professional problems which are modeled on the MCAT. They're multiple choice questions. They're answered in the back of the book. And so if you do all of those pre-professional problems, those are similar in content and format to what the American Chemical Society exam will be. There is material from the ACS that you could go to their examinations website, and there's a study guide, but it's not very useful because the ACS study guide isn't specific to the first semester course, which means there's all kinds of second semester material in there that you have to figure out how to ignore. So I don't recommend using the ACS study guide. It tends to be demoralizing because there's so much stuff in there that you haven't seen before and you have to have no clue. I think the pre-professional problems at the back of the chapter will be the best way to study for that.